Yeah.
So this is a basic outline of what we're going to be going over. We'll look at some of the features of the Cross V2. We'll dig into the implementation, in particular, look at the smart contracts, some example transaction flows. We're going to spend a lot of time discussing bundles and how bundling works in a Cross V2, which is kind of one of the core concepts of how everything works and kind of what makes it a unique product versus a competition. We'll look at some of the other implementation details, discuss some hard problems, and close with some resources that you guys can look at, as well as useful content for people that might not be part of the UMA team when this becomes a video on YouTube. So to start with, let's look at some of the features. So a Cross V2 primarily is a layer anything to layer anything bridge. Wherever we have a canonical message and token bridge, we can deploy this mechanism. Which is really cool. And this is obviously the main difference versus V1, which was only a fast exit bridge. Another feature that's important is that all the funds in V2 are concentrated on layer 1. This gives us much higher capital efficiency, and we'll dig a little bit more into this later, why this is important and why it's cool. It has very low gas costs for depositors, lower than V1, which is important. And equally, the costs for a relayer are also lower than V1. The execution of a relayer bot is designed to be very simple, and the actual implementation of the relayer bot is much simpler than in V1. And this we kind of achieved through the separation of concerns between different roles in the system using different actors. And we've also managed to maintain a very simple integration with the optimistic oracle. We only really have one kind of price request, and everything stems from this, which is also a feature in its own right, because it makes it somewhat easier to reason about some of the security assumptions and to understand how the system is working. So this is a high-level overview of the smart contracts in a Cross V2. We're going to dig into each of these contracts independently. But to begin with, I think the most important thing to realize is that we have this thing called a hub contract, which sits on Ethereum layer 1. It contains all the liquidity, and it communicates with these things called spoke pools, which sit on the layer 2s. Ethereum layer 1 also has its own spoke pool, and that's just for separation of concerns. And basically, anytime there is a relay, a deposit, or a fill, any sort of actual relay action, that happens via the spoke pools. And all the sort of administrative pool rebalancing, relayer refunds, all the logic that's not just for deposits and fills happens in the hub pool. We then have these adapters, which sort of sit in between the hub pool and the spoke pools. And the hub pool also connects, obviously, to the optimistic oracle for validating actions within the system, which we'll dig into the details of that later. Before I go on, I just want to say, if there's anything along the way that doesn't make sense, that's okay. I've sort of set these slides up in a way where it will be a bit repetitive, where we look at a high level and then we sort of drill down into things as we go. So if things aren't immediately obvious in the beginning, that's okay. Just let's roll with it, and things should make sense as we go. Okay, so I spoke a little bit about the hub pool, deployed only on Ethereum layer 1. It stores all the liquidity of all the depositors. So whenever LP deposits or withdraws, this is where they do it. It is responsible for tracking all the LP fees that actually accrue to the liquidity providers. It's the main interaction for this actor that we call a data worker, which we'll get to a bit later. But basically, the data worker is responsible for actually managing how the system or the protocol works at large, around how we rebalance pools, how relays are refunded, and are also responsible for slow relays. And we'll get into that a bit later. This is also where disputes happen, is in the hub pool contract. The hub pool is also this sort of cross-chain administrator of the entire system. So it's responsible for governing the spoke pools, and it can instruct the spoke pools to send money back to layer 1, which we call a pool rebalance. It's owned by the cross-DAO multisig. And this is important because there are a number of settings in the hub pool that govern how the protocol operates, including a fee capture mechanism. So obviously, the ability to change these settings is very important, and therefore it's controlled by the cross-DAO multisig. In the future, maybe that changes to a more sophisticated mechanism, but it's designed in a way where we can sort of swap this out. We spoke about this spoke pool thing. So this is deployed on all the destination chains in the system, including Ethereum layer 1. And basically anywhere you want to send money from or to is a spoke pool. So we'll have one on Arbitrum, one on Optimism, one on Boba. Every chain has one. And a user will deposit funds into a spoke pool, and a relayer will fill these deposits in the other spoke pool. Sort of the nomenclature we use to describe this is an origin chain and a destination chain. So if you're relaying from Optimism to Arbitrum, obviously Optimism is the origin, with Arbitrum being the destination, right? Origin and destination. The spoke pool is controlled by the hub pool, and the hub pool can send specific instructions to the spoke pool to indicate or to instruct it to do certain things, such as sending funds back to layer 1. And we'll get to what that looks like in a little bit. The hub pool can also instruct the spoke pool to refund relayers after fills. And finally, the hub pool can also instruct the spoke pool to fill slow relays. And this will happen when the relayers actually run out of money and we need to do a slow relay. It's kind of analogous to what we had in V1, but a bit different. We spoke about these chain adapter things. So sort of at a high level, we have one of these per destination spoke pool. These are deployed on layer 1, and they basically act as an abstraction layer to sit in between the bespoke interfaces that each of these chains have and the hub pool. So it basically gives us like a unified interface so that the hub pool only needs to know how to do one kind of thing, and it can talk to many kinds of layer 2s. Arbitrum and Optimism, for example, have different interfaces for sending messages and sending tokens. So this thing lets us sort of unify that. And it can primarily do two things. It can send tokens to the destination chain, as well as send messages to the destination chain. And the reasons for those are pretty clear. Either we're rebalancing the system, so we're sending money to the layer 2s to actually refund relays or do slow relays, or we're sending messages to tell the spoke pools to do something such as repay a relayer, or to send money back to the hub pool. We have this thing called the config store. So the config store basically stores settings of how the system operates. We have rate models stored in it. We have token transfer thresholds and a bunch of other stuff that governs how the data worker works. And this is owned by the cross DAO because obviously it sort of governs how the protocol operates. Don't need to go into too much detail for this. Okay, so that was a lot. I know. Sorry for dumping that all at once, but we just need to get through that so we can get to sort of the intuition part of the slides. So before we go into any detail on how the bundling works and like starting to understand how these contracts actually operate, I want to go through some simple examples of like the most common flows within the contracts. And I think maybe we can use this to build an intuition around how these contracts work, and then some of the stuff later hopefully will make a bit more sense. So let's go through a very simple fill. A user is on Optimism and they want to send money to Arbitrum. So first thing they do is they call the deposit method on the Optimism spoke pool. And in this method, they specify some parameters, which are the recipient, so who's going to receive money on the other side, the origin token, so if they're sending USDC, in this example, that will be the USDC address, the amount that they want to send, the destination chain, so that'll be the Arbitrum chain ID, the relayer fee percent, so what percentage of their deposits do they want to send to the relayer to incentivize them, and then the quote timestamp, which is basically just there to make sure that the user isn't doing anything weird and that they have like strong guarantees around the actual prevailing realized LP fee percent that they're going to receive. So when they make this deposit, we emit an event, and then a relayer on the destination chain sees this event. They can say, okay, cool, this looks legit. I can see the deposit. It looks correct. The money is in the spoke pool. I'm now going to fill the deposit. So they call fill relay on the destination chain. They specify all the parameters. Everything there is the same as what the depositor put, except for realized LP fee percent. So the realized LP fee percent is basically the amount of the deposit that's going to go to the LPs for servicing the protocol, for actually facilitating the loan, which we'll get to a little bit later. But if you know anything about across V1, that parameter shouldn't be that exotic to you. One thing to note here is that this can happen with multiple fills. So we do support partial fills in V2, which is cool, and kind of an important detail when it comes to slow relays. And another thing, which we'll touch more on later, there's only one fee parameter. In across V1, there was a slow fee and an instant fee. Now we only have relayer fee percent. We'll dig into why that is the case later, but just it kind of simplifies the interface and makes things simpler. So this is the simplest flow in the case of a fill relay, a relay being completely filled, which will probably be like 99 or 95% of the time. Let's go through now a slightly more complicated example. In this example, we're going to look at a partial fill plus a slow relay, and then look at how the relayer gets their money back, right? Because this is an important part. The relayer has done something, they've spent money, and ultimately they need to be refunded for those actions. So as before, the user calls deposit, they specify their parameters, we emit an event. On the destination chain, the relayer calls fill, they fill the relay. So nothing has changed at this point. But now let's assume that the amount that they're actually filling is not the total amount. They've partially filled the relay. So what happens now? So now what happens is we introduce the data worker, this actor we discussed earlier. So what they do is they construct what we call a bundle of data, which consists of 3 different kinds of information, and we'll get to the information later. But for now, just consider this as a set of instructions that tell the spoke pool what to do. So importantly here, we're considering the slow relay route. The slow relay route is basically going to instruct the spoke pool to fill the amount of data, the amount of the fill that the depositor didn't, that the relayer didn't do, to fill the remaining amount. I love getting paged during presentations. So yeah, we construct the slow relay route, which will actually fulfill the remaining amount of the relay that the relayer did not fulfill. And we can construct this bundle and then actually send it across the canonical bridge. So the hub pool sends a message over the canonical bridge, and this includes the actual funds to fill the shortfall, right? So the relayer couldn't actually fill the relay in totality. So we send the remaining funds over the bridge to the spoke pool to actually fulfill the remaining component of the relay. So when this gets to the spoke pool, we can then call execute relay leave or execute relay refund leave, and this will repay the relayer, right? So that's the important part. We repay the relayer, and we also store the slow relay route, which is used to actually fulfill the remaining component of the relay. And when we actually we then execute the slow relay leave, and this pays the recipient. Okay, so there's a lot of like interfaces here in code. I think the important detail that I want, the intuition I want you guys to have from this is when funds can't be completely filled, we can fill this using the hub pools funds, and we're starting to slowly introduce these concepts of these bundles, right? And all you need to think about in terms of the bundles at this point is that they're instructions that can tell the spoke pool what to do, right? And in this case, they are distributing some funds to the relayer, and in this case, they're actually filling the remaining amount of the deposit that wasn't filled by the relayer in the beginning. We'll go into how they're constructed later and look at the details, but yeah, for now, that's sufficient. So yeah, bundles, right? All these bundles, and we got bundles in bundles, and we're gonna get to all the details of these in a minute. So let's dig a bit into that. Actually, before I do that, Matt, Nick, anybody else, do you guys want to add any details at this point before I go into more details on the bundling?
Only thing I'd say is maybe it's a good time to open it up for question, like a kind of middle point for questions to see if anybody is confused about anything.
Yeah.
The depositor determines their relayer fee percentage. Is that inclusive of the LP fees and the relayer fees, or does the LP fee completely determined at the time of like relaying?
Good question. So the depositor defines the relayer fee percent exclusively. The realized LP fee percent is dictated by the protocol as a function of the pool utilization when the relay is filled. We're going to look at that a little bit later, but that's functionally equivalent to V1, right? So when the relay is actually filled, we look at how much money is in the pool, what percentage of that is utilized, and considering your deposit, how much are you going to influence that utilization, and that gives you the realized LP fee percent. So they're separate things. Another feature that I guess we can touch on now that isn't included in the slides, across V2 does support speedups. So a depositor can choose, if their relay is not being picked up, to increase their realized relayer fee percent. So they can basically resubmit a signed message signaling that they want their transaction to be sent again at a higher fee, which is kind of cool. And this works basically the same way that like any Ethereum transaction speedup would work.
Okay, thanks. Are there UX concerns or like front running concerns around the depositor not actually knowing what they're going to pay in LP fees before depositing?
Yeah, I mean it's a hard problem. It's kind of like first price gas auction before we had 1559 in Ethereum. But the goal, I think, is that the front end will basically always get this like close enough that they're not overpaying and that the relayers are not getting ripped off. So yeah, but ultimately that's up to the relayer to choose whether or not they're going to actually fill the relay. So and if you like undersend this, you can always relay it yourself. So there's never a situation where like you underpay it and then it gets stuck and you lose your money. So you can always like fill it yourself and you can always speed up the amount. So yeah, and it becomes very difficult when there's like capital crunches, right? When like the system is running low on money, relays are depleted. But yeah, that's kind of a hard problem. But our solution really is like the front end will give like good estimates in terms of these fees, and you can speed them up. And yeah, we'll dig a little bit more into like how we're thinking about the fees a little bit later. There's like a whole section on that, but yeah, it is a hard problem.
Cool. Thanks, Chris.
Okay. So I'm just going to keep it going and we can like have a big section at the end for questions. So let's talk a little bit about bundles, right? This really is the crux of Across V2. These things that I sort of glazed earlier and described them as like things to instruct the spoke pools on what to do. Let's dig into what those actually are. So the bundles are, and the way we use bundling is the reason that Across V2 is fast, efficient, and pretty cheap compared to V1 and compared to other products. So this word is a bit overloaded though. And I think we should try and distinguish between the three different kinds of bundling that we do in Across V2. So the first thing is data bundling. And this is basically where we use compressed data structures in the form of Merkle trees to compress the information we need to put on layer one and the information we need to pass between the different chains. We also do bundling in the form of sending batch transactions using multi-call. This is the same as in V1, where we can send multiple relays at the same time, but we do this even more aggressively in V2. And we also bundle liquidity in the form of putting all the liquidity in one place on layer one. So yeah, it's an overloaded term, but it is kind of like a good way to describe this. And yeah, we'll go into each of these now. So let's talk about Merkle trees. And I'm not talking about this kind of Merkle tree. I'm talking about this kind of Merkle tree. So a Merkle tree is a data structure where every leaf, which is the bottom row of the tree over here, sorry, every node, the slide is actually technically wrong, but yeah, every node is a data block, and every leaf leading up till the root of the Merkle tree is the hash of the layer below it. So we take data 1, data 2, data 3, data 4, we hash those, and then we hash the hashes all the way up until we get to the root of the Merkle tree. So that's the basic structure. And we can then generate something called a Merkle proof. Now, a Merkle proof is used to prove inclusion of a leaf in the original data set. So what this means is I could give you a proof plus data 3, and you could prove to me without any other information in the data set that the leaf that you gave me is part of the broader data set. So for example, you could like have a massive set of transactions, and I can give you one transaction and the proof, which is concise in that it's short, and you can prove with complete guarantees that that original transaction is within the set of transactions or the piece of data, right? It can be anything. You can use this to prove that a row is in a spreadsheet. If you take each row in the spreadsheet, hash them, and then hash the hashes all the way up to build a Merkle root. And this is important because, like I said, with simply having the proof and the root of the Merkle tree, you can construct this concise inclusion proof. And the proof size is logarithmic in the size of the tree. And this is really why Merkle proofs are and Merkle data structures are so important and so powerful, is because this logarithmic scaling means that, like, for example, a tree with 8 leaves only needs a proof size of 3, but a tree with 100 million leaves only needs a proof size of 27. So I could give you one random leaf out of the 100 million data set and a proof of size 27 byte, an array of 27 byte 32s. And I could prove to you that that leaf is within the broader set without you needing to have any of the other elements in the tree. Okay. So the way the proving basically works is you need to have the root of the tree. And I could prove to you that C is in the tree by providing you with D, the hash of these ones and the hash of these ones. And we don't need to go into like the big detail on why this works or any of the cryptography. All that matters is that just consider that if there's all these different things in the tree, and I want to prove to you that this thing is in the tree, I don't need to give you a whole bunch more data than just like some path that basically traverses up the tree. So like I said, the only thing you need to know is the root of the Merkle tree and the proof. And why this is really cool is what we can do is store the root of the Merkle tree on chain and a data structure called a bitmap to actually signal if that leaf in the tree has been claimed or executed or whatever the case may be. So like in the case of the Uniswap token drop, each recipient, right, if you got tokens from the Uniswap drop, each recipient was a leaf in the tree. And then when you actually claimed it, you use this bitmap to show like recipient 600,554 has claimed, right? And you kind of flick a bit in the smart contract and you prove that that thing has been claimed. And the actual validation of these proofs is really simple. We use a library. We don't have to do anything fancy. And this is kind of an example of what a proof might look like. It's literally an array of bytes 32, which grows in length the bigger the tree. And like I said, these things are used in Ethereum. They're called Merkle Patricia trees in Ethereum, which are used to store all the different kinds of the state and transaction receipts, transactions and transaction receipts in separate trees. And also used in token drops. So we've used this before at UMA for our TVL token thing that we did last year, and a bunch of different projects have used them. And like I said, the structure with that is that each leaf in this data structure would be basically your claim, like the tokens that you're entitled to, maybe the action that you did, and then you go to the smart contract, you present it with this proof thing, right? We use the OZ library to verify that that was part of the tree. So the smart contract only needs to know the root and the proof, and then you can prove that you were part of the original set. And then we flip the bitmap to actually say that it's claimed. Okay, so there's a random data structure. Why is this relevant to Across V2? So in Across V2, we use this for all of our data bundling, which was the first class of bundles that I referred to earlier. There are three different kinds of bundles that we use. There's a pull rebalance bundle, which is used to push funds to and pull funds back from the spoke pools, right? If we remember the contract architecture we had before, the hub is instructing the spoke pools to send money to them or to pull money back from them. That's what a pull rebalance route is. And this, when I talk about like the pull rebalance, we construct a Merkle tree where the leaves are the instructions that do these specific actions, right? So then the second kind is a relayer refund. And this data structure informs the spoke pools on how they should repay the relayers for valid fills that they did against deposits. So for every deposit, like we went through in that example in the beginning, for every valid deposit and fill, there will be a relayer refund leaf that tells the spoke pool to pay back the relayer for the action that they did. And then the third kind is a slow relay. So slow relays instruct the spoke pools to fill a deposit that was not completely filled by a depositor, sorry, by a relayer, which would be the case if we've run out of funds or just the system is at super high load or whatever the case may be. Relayers go offline. Okay, bundles. So let's go through each of the kinds that we discussed before in turn and discuss them slowly and break them down. So the pull rebalance leaf and the pull rebalance bundles. So the pull rebalance leaves, right? There are multiple leaves that goes into a tree and the tree constructs a bundle and we have a bundle of leaves, okay? So pull rebalance leaf indicates how the funds should flow to and from the spoke pools. So funds are pulled back from the spoke pool to the hub pool when the amount of funds in the spoke pool exceeds a configurable percentage of the total system funds, right? And we call this the token transfer threshold. We saw this in the token config store. in like slide 4 or something, which I kind of glazed over. But basically this number says if there's more than a certain percentage of funds in the spoke pools, then they should be pulled back. And the pool rebalance leaf is going to instruct the spoke pools to do that, right? So let's have a quick example. You have like Ethereum, Optimism, and Arbitrum, and we basically say that we want the spoke pools to never have more than like 25% of the money in them, right? All the remaining funds should sit in layer 1. So in the event that we get to 26%, then we can construct a bundle. The bundle gets sent to the spoke pool. We execute the bundle, and it sends money back to layer 1, right? So that's the basic idea. And then funds are pushed to the spoke pools, which is also part of the pool rebalance leaves, when we execute a repayment on that chain or we execute a slow relay. So a relayer repayment on that chain would happen if a relayer chooses to be refunded there. So this detail I didn't really mention earlier, but when a relayer fills a relay, they can choose where they want to be repaid. So relaying from Optimism to Arbitrum, the person who fills the relay on Arbitrum could say, hey, I want to be refunded on Arbitrum, right? Which is where they spent their money. That might make sense. But maybe they want to be refunded on Boba, right? Because they want to rebalance their inventory. Or maybe they want to be refunded on Ethereum layer 1 because they want to concentrate their liquidity on layer 1 and then distribute it when they need it. So there's a lot of flexibility for the relayers in this regard. And finally, the pool rebalance leaves contain information around how LP fees accumulate over time. So this slide we're not going to go into, but just to show you the basic data structure that's in the smart contract. And this is like each of the components here are what we just went over. Okay, relayer refund leaves. So the relayer refund bundles and the leaves within those bundles are used to inform the spoke pool on how to refund a relayer for a given set of valid fills. Okay, so there's been a set of valid fills, and we create a bundle which says refund this relayer this amount of tokens of this token type. And importantly, here's where we get some sort of bundling within bundles. The relayer will receive the sum of payments from all previous within a time range of previous refund bundles. So what I mean by that is, let's say the relayer has done 10 fills since the previous bundle, all of the same token, right? So there've been 10 deposits on Optimism or 5 deposits on Optimism, 3 on Boba, 2 on Arbitrum, all going to one place or maybe going somewhere else. And the relayer is chosen to be repaid for all of those fills that they did on Ethereum layer 1. So we can basically add together all of those repayments and just do one transaction, right? So you only need to repay the sum of the fills, right? So you have this sort of bundling of repayments within the relayer refund bundle, right? So bundling within bundles. Again, like I said in like the original contract slide, if this doesn't make a huge amount of sense, it's okay. We're going to go through an example in a little bit. This is the data structure. These are the components that I spoke about: amount to return, the chain ID where the refunds are executed, leaf IDs, all these kinds of things. And then finally, we have the slow relay leaves. Okay, so the slow relay leaves act to fill deposits that weren't completely filled by relayers, right? So in the event that there's a partial fill, say our relayer only has like $2 million worth of USDC, right? And there is a $5 million relay. We would construct a slow relay leaf that would instruct the spoke pool to fill the remaining amount of the remaining unfilled amount of that relay. So in this scenario, we would push funds to that spoke pool, and then when we actually execute the slow relay leaf, it will send whatever the unfilled amount is at that point to the recipient. And I think that part is quite important at that point, because there could be subsequent fills that happen after that 2 million that we originally did. And we only want to refund or to fill the remaining amount that wasn't completely filled, right? So you don't want to overfill it. So yeah, the slow relay leaves enable us to do this. And again, data structure, more just for reference if you guys want to dig into it a bit more deeply. Okay, so let's go through the example that I was talking about. Once we've gone through this, we can have some questions and we can go over it again because I know I'm rushing through this, just there's a lot of content. Okay, so let's consider the evolution of time here, right? We have stuff in the past over here, previous bundles. we have a sort of peg in the sand, an artificial point in time where we say, I am evaluating from now until the current block number, right? And this peg in the sand is influenced by the previous data workers bundle that they created. They say something like, my bundle, so like the previous bundle, ends at the certain block number. So when we create the next bundle, we can go from that peg that they created up until present, right? So there's a definitive slice in time. So the data worker looks in this interval and they look for all the valid fills within that period of time, okay? And a valid fill means that each of the deposit properties that was added by the depositor on the origin chain matches to the fill properties that the relayer put on the destination chain. And importantly, that the realized LP fee percent was calculated correctly, because that's calculated by the relayer. The depositor does not specify that. So the depositor, the relayer basically needed to have done their job correctly, right? So the data worker looks over the interval and they say, okay, cool, these fills are all valid, right? And we can look at these. We can say, you know, they're all from the same depositor. Okay, cool. The recipients are the same. And importantly here, we have two different relayers, right? These two addresses are the same and these two addresses are the same. So we've got two groups, and we have 3 relays with USDC and 1 of WETH. Okay, that's also important. And the repayment chain for all of these is Ethereum, which I think I changed to Arbitrum later, but let's just go with what the slide has now. Okay, so that's step 1. The data worker collects all the valid fills within the time frame, right? They can filter out anything that's noise. Step 2 is they're going to group them by the relayer and by the token, okay? So this is to say that these two cannot be grouped any further because they're separate tokens, right? The relayers are the same, but the tokens are different. These two can be grouped because the tokens are the same. They're both USDC, and they both were filled by the same relayer. And this is where the summing thing that I mentioned earlier comes in, right? We don't need to repay 2 separate payments here. These can be done in the same payment, so we can group them together. So step 2, we group the repayments by relayer and by token. Step 3, we construct the Merkle tree that we spoke about earlier, right? So the very base of the Merkle tree are the actual data blobs, right? The repayments that we just constructed in the grouping stage before. So we construct the base of the tree. We then hash all the way up to get the root of the Merkle tree, right? And by proxy, in the same process here, we're going to construct the proofs, right? And we'll keep the proofs for later. We don't need to worry about that right now. What matters now is we have the root of the Merkle tree. And this root of the Merkle tree is like this condensed data structure that in and of itself represents the correctness of the relayer repayments, which them in and of themselves represents the correctness of the fills. Okay. So we now have the root of the Merkle tree. Step 4, we go back to this like similar variant on the diagram we had seen before. So the data worker goes and calls propose root bundle. And now we can actually dig a little bit more into these props that we glazed over earlier. So the bundle evaluation block numbers, this is the peg in the sand that I mentioned earlier on, right? It's the data worker saying, I'm evaluating the things that have evolved over time up until this particular point in time. They need to specify how many pull rebalance leaves there are so that we know once all of them have been executed. They specify the pull rebalance route, which indicates how the funds are flowing to different parts of the system, like we mentioned. And importantly, the relayer refund route, the one in bold here, which is the one that we constructed in the previous set of slides, right? Because we're considering in this example how the relayer refund routes are constructed. In submitting this bundle, they are bonded. Okay, and we use the optimistic oracle to verify the correctness of the set of routes. So any one component of the routes could be wrong. And if they're wrong, then they're going to get disputed and it'll go to the DVM and we arbitrate in the same way we do with every other product in the UMA system. And that entails, you know, a vote and the resolution, and then either the bond goes back to whichever party was correct, either the proposer or the disputer. There's some details here about how we do the bundling of proposals, which we don't need to go into, but I will just mention one thing, and that's that the design can only ever have one set of routes in liveness at any point in time. We don't allow to have multiple proposals at the same time. And the reason is just consider how hard it would be to reason about overlapping proposals. So if you have one data worker that was evaluating block number 10 through 15, and another data worker was evaluating block number 10 through 16, they're both technically valid, but as soon as the one bundle is considered correct, then immediately the second one becomes considered incorrect. And there are all these sort of like weird timing things that happen. So in the implementation we have on mainnet, there's only ever one bundle in liveness at one point in time, and you can only propose a new bundle once all the leaves in the previous bundle have been executed. Okay, so we've got this relayer refund route that we constructed in the Merkle tree. That's now proposed. It's now in liveness. Let's say it's valid. No one disputes it. Excellent. We now get to the execution stage. So when we execute the bundle, what we do is we bring on chain the entirety of the leaf that was at the root, at the base of the Merkle tree, as well as the proof that we discussed before, right? And you need to provide the entire contents of the leaf because you need that to actually reconstruct the components of the Merkle tree to actually prove inclusion. Okay, but you only need to put that in core data. We don't actually need to store it on chain, so it's not that expensive. The same thing happened with your Uniswap token drop. When you actually clicked claim, what was happening behind the scenes is that you were showing the smart contract, this is how many tokens I'm entitled to. This was my claim identifier, and here's my proof. And then the smart contract like hashes the leaf that you presented it, and then uses the Merkle proving library to prove that that data that you presented was part of the Merkle root given the proof. Okay, so we've proved that the leaf is correct, and then we make the cross-chain call. So we now say to the spoke pool, hey, here is the relayer refund route, right? That's the thing in particular that we're tracking in this example. And here is the money to actually refund the relayers, right? For all of these valid fills. So here's the money, and we send it over the canonical bridge, right? We use the optimism or arbitrum bridge in this example. We send it over the bridge, and we send the message to relay root bundle, which is the function in the spoke pool, which actually adds to the spoke pool a specific relay refund route and a specific slow relay route. So these data structures are what is actually in the proposal phase here, is what is encoded or enqueued into the arbitrum or whatever the chain's spoke pool that can be executed later down the line. Okay, so now the spoke pool has the roots of these Merkle trees. We can now do the execution of the leaves. Okay, so we glazed over this before. We're going into more detail now. What actually happens, like I mentioned, is that the data worker will provide the entire leaf, right? The relayer refund leaf. And that screenshot that I had of the code, they literally provide every element within that data structure in this call data, okay? As well as the proof, the inclusion proof that we created in step 3 that actually proved that that leaf was part of the broader data structure. So you provide this information to the spoke pool, we execute the relayer refund leaf, and then it actually does the thing. So in this particular example, the thing is to repay the relayer, right? And it's going to repay them the sum, if it's this relayer, the sum of the two relays that they did. In this, if it's for this relayer, there'll be two separate relayer refund leaves, and they will need to be executed separately because they're doing separate things. The one is sending USDC, the other is sending WETH, right? So each of these relayer refund leaves can be executed, and importantly, they all fall within the same proof. Sorry, not the same proof, the same root. So each leaf has its own proof, and they all fall within the same root. So this method will be called for each leaf that we constructed in the previous stage. And at this point, we've refunded the relayers. Okay, so that was a lot. This only went over the relayer refunds. I'm not going to go over how the slow relays work and the pool rebalance work because it's kind of similar. And this one is kind of the most sort of illustrative example of the design. So bundles, okay, that was a lot. Let's do another round of questions that anyone has perhaps, and then we can go on to talk about other components of the system such as fees.
Awesome, Chris. I had a quick question. The data worker and kind of all the stuff with the Merkle, I don't know, there was a lot of stuff you were showing. That's all bot infrastructure? That's not smart contracts?
Yeah, all of this is off-chain. The only part that's on chain is the blue and sort of teal diagrams where we actually are submitting this information. And that's like a really good question because we can illustrate some of the compression stuff, right? Because you have all these different fills that are condensed into these smaller repayments. And this data structure could be massive, right? We could have like 100,000 relayer repayments, right? Like in the example we had before. And the only thing we need to bring on chain are these roots. That's it, right? So that's where the compression comes in, and that's why the bundling is so powerful, because we only need to provide the roots of the Merkle trees.
And those roots are the thing that we use to validate whether a repayment, well, I guess it probably does a lot of things, but it also does validating whether a repayment request is justified.
Absolutely. So you could have these three roots that do basically an infinite amount of actions, and you only need to look at 3 bytes 32 values to validate the correctness of all of the information within them. So I can independently look at the fills that happened over the interval, right? Or maybe the slow relays, or maybe the pull rebalances, right? Depending on which of the roots we're talking about. I can independently look at those, reconstruct them, and then say, did the roots that you provided the smart contract, do those match to what I think they do? And if they do, then everything is good, right? I don't even need to know the data within the roots. I can just say that they're correct, right? And that's, again, where the compression comes from, because it's lossy compression. But all the information that we use to get to that point is publicly available. So anyone can independently verify it. And then if it's wrong, if even like 1 byte within the bytes 32 mismatches, then the entire bundle is invalid and everything is disputed. And then you need to try again.
That was kind of another question I had. Sorry. So there's a dispute. If there's a dispute, then other bundles, other transactions that aren't actually being disputed will be tied up for the entire dispute.
So the way that we do disputes here is that we throw out the invalid bundle, we delete it effectively, and we send the arbitration of that to the DVM. And once the DVM comes back with a result, how the bonds are paid and like who gets their money, everything is handled by the optimistic oracle. As soon as we delete it, though, a new bundle can be proposed, right? So let's say it gets disputed 2 minutes into liveness, right? Which is probably what the case would be, or maybe 5 minutes into liveness. As soon as it's disputed, another bundle can come in. So you can't actually like hold the system ransom unless you continue to keep paying the bond. And the bond is going to, in theory, be a lot, right? It's going to be in the order of like, I don't know, 50 ETH, probably, maybe less to begin with. But in the long arc, it should be like a high number to disincentivize that. So you can't really hold the system ransom like by blocking the evolution of the system unless you're willing to just delete money.
Cool. Thanks.
To this example you said, comes another question for me. So if let's say in a bundle, a transaction is falsy and everything is disputed, this transaction is consuming money, actually. That's why it's not included in the next one, or maybe another one bundle. Correctly?
So if one of the data points within the bundle are bad, like let's say that the relayer, the data worker was trying to steal money from the system, right? They could create a fill in the bundle that's wrong, right? Let's say they just want to they say pay, like I'm the recipient, I'm the relayer, and like I'm entitled to 1,000 ETH, even though there was no fill, right? So they add in an invalid component within a set of other fills, right? So in that case, all of the fills are considered invalid until you can provide a bundle that excludes the invalid fill. So that one where you're trying to steal money from the system needs to be excluded, and only when that's excluded can the rest of the fills be executed. Does that answer your question?
Yeah, kind of. So it's never included again on another bundle when another try is being submitted, right?
Yeah. So the invalid one will be excluded, but all the valid ones that have not yet been included, right? Like, let's say that those will be put into the next bundle.
Yeah. Okay. Yeah. I get it. Thanks.
I'm probably just misunderstanding something, but like, why would there ever be leftover funds in spoke pools if all funds sent from hub pools to spoke pools are for either slow relays or paying back relayers? And then all user funds are just sent directly back to the hub pool.
So the last part of the last sentence there is the reason that I think you might be confused. All user funds are not sent back to the hub pool. They sit in the spoke pool until the hub pool tells them to come back, right? So if you deposit on Arbitrum to go to Optimism, your money will sit in the Arbitrum spoke pool until the hub pool instructs it to go back to the hub pool. And that's potentially a good thing, right? Like if the flows are equal and we can do some kind of netting, then we can leave money in the spoke pools and we potentially don't even need to send that much or even any money from layer 1 to the layer 2s to do the refunds. So yeah, I think the important detail there is like money is not sent to layer 1 until the hub instructs the spokes to do so.
Gotcha. So it's not like a cross V1 where it's automatically sent over the like canonical bridge at like, well, actually, I guess it is similar at like some threshold it is.
Yeah. There's some slides on this particular detail around netting a little bit later, but yeah, that it's different in that it doesn't just happen automatically. It's only happened when the hub tells it to do so, and like the rules around that are informed by the UMIP and ultimately governed by the cross DAO.
Cool. Thanks.
I have a question about like fills within a certain time period. Let's say you have 3 origin chains and one of them has some downtime. And so like those fills are not going to be reflected in a particular bundle. Do they get added to a later bundle where it's just like all the fills that were not previously included in a previous bundle or something?
Yeah, that's exactly right.
Okay.
So this data property bundle evaluation block numbers is an array of block numbers ordered by chain ID, right? So like chain ID 1 is Ethereum, 10 is Optimism, etc. Right? So it's basically saying the bundle that I'm proposing covers the following block range from the previous valid evaluation number, right? And if let's say Boba is down, then perhaps that chain ID in this array simply does not increment, right? So like it could be equal to the previous bundle evaluation block number for that particular chain, like 288 for Boba. But yeah, like part of the rule is that at least one of the chains must advance, because if that's not the case, then you could provide bundles that are valid but do nothing. And that kind of like links a little bit to like Clayton's question around like holding the system hostage, right? Like I could just continuously propose bundles that do nothing. So a rule is that like at least one bundle, one chain's worth of block numbers must evolve. And other ones can stay the same, which would be the case if there was no activity on the chain or the destination chain is down. Okay, I'm gonna keep it going because we like running out of time and there's still a bit of content to get through, and I'm sure there are more questions. Okay, we're done with the bundles. Oh, we're not done with the bundles. Haha. Okay, so bundling of transactions. We can keep this one quick. We can send multiple actions in one transaction. This is the same as in across V1, right? So you could send like a few relays at the same time, or in the case of across V1, we do settlements and relays at the same time. All very nice and cool and cool and all that. Saves gas, cheaper, very cool. Bundles. The final thing of bundling is bundling funds onto layer 1. So, right, we've discussed this a bunch, right, around aggregating the liquidity on layer 1. And this is obviously very important because it means that we don't fragment our liquidity. And this is a big problem with a lot of the other bridges that are out there right now, where you basically, for every chain you bring on, you sort of decrease your capital efficiency by splitting up the money. So in across V1, we move the capital efficiency basically somewhere else. We haven't magically solved this problem. The problem basically just ends up on the relayers, which we'll get to later. But we basically aggregate all the funds onto layer 1. And to your question, Sean, around like when we actually send money back and forth, this is influenced by this token transfer threshold, which specifies when we take money from the spoke pools, bring them back onto layer 1. So a little bit more about netting, right? So in a perfect world where we have symmetric capital flows, where money is moving to and from all the chains, we don't really need to do many pool rebalances, right? Especially if the relayers are choosing to be refunded on the same chain that they actually sent money from, right? So, user A sends money from Optimism to Arbitrum, and user B sends like about the same amount in the opposite direction. We never really need to do any pulling or pushing of funds. But in reality, we don't really think that's how the world's going to play out. It's likely that yield is going to dictate where money flows across this ecosystem of rollups. So we've kind of tried to design the system to be to kind of accommodate both scenarios, where we have the sort of happy path of symmetric capital flow, as well as asymmetric capital flows, where the system can rebalance itself and move money around where it needs to go. And I think an important thing in this is it's like really hard for us to know how this is going to behave, right? All we can really do is create a system that can accommodate both scenarios and put some levers, some magic numbers into the protocol that we can adjust as the protocol evolves over time. We're going to have to see how this goes, right? So we can kind of pick the best numbers that we think are reasonable, right? Maybe 5% is the right number to leave money on the spoke pools. Maybe it's 20%. I don't know. We're going to have to experiment and see what makes the most sense and kind of and ultimately optimize for what gives users the best experience, right? And that's gonna require us to experiment over time, and we can do that, which is kind of cool. Bundles. Okay, we're done with bundles, thank God. Let's go through some of the remaining components. Nothing as complicated as what we've gone through now. The rest is all quite a bit simpler. So in across v2, tokens flow across what we call a route. So a route is an origin to a destination. And depending on where you're sitting, that can change. So if I'm on Optimism, everything else is a destination and Optimism is the origin, right? But if I move to Boba, then Boba is the origin and everything else is a destination. And this is important because a lot of tokens within this ecosystem of rollups or ecosystem of layer 2s are not going to be deployed everywhere, right? So Badger, for example, is not on Boba, right? And UMA is maybe not on another chain. So we need to be able to conditionally enable and disable specific token flows within the system. And this is also important when it comes to one of the chains potentially breaking. Maybe you want to disable tokens flowing in one direction, but not in another. Downside, though, is this diagram, and you can see how many lines it has. And there are basically n times n minus 1 routes per chain per token. So I'll say that again. There are 20 routes in our current setup per token. So just with USDC, there are 20 routes. If we add in WETH and Wrap BTC and Boba and all these other tokens, all of a sudden we have a lot of routes. Kind of okay, though, because we can enable a whole big batch of routes all at the same time. We can do this with multi-call, and we've got some like really nice scripts to do this for us. But yeah, so routes, that's basically how we think about the system and how tokens flow within the system. Okay, let's go back to fees. So we spoke a bit about this. There were some questions that like prompted some discussion, but let's go through it in a bit more of a structured way. So ultimately, fees in across v2 are a simplified version of that in v1. We intentionally tried to make them easier. They were kind of weird in v1. So in v1, you had both a slow relay fee percent and an instant relay fee percent. Right? This is complicated. Like, why should I need to distinguish between the two of these? In across v2, there's only relayer fee percent. And what's kind of cool is a slow relay is done by the protocol in a sense, right? Where the hub pool is actually refunding you for your money. So we don't actually need to define this percentage because it's 0. So in across v2, if your funds are slow relayed, you actually get a refund for the relayer fee percent because there is no relayer. You only pay the realized LP fee percent, which we'll come to in a second. So if we have a simple example, you want to send 100,000 USDC, you set your relayer fee percent to 1, half of it's relayed by a relayer, the other half is slow relayed. So in this scenario, half of it times by 0.01 or 1% is $500 in fees. So the depositor will immediately get 49,500, right? Half the money minus the 500 in fees. And then when the slow relay bundle is actually executed, they'll get the second half of the money and they'll be refunded for the slow relay component of that. So they'll get the full 50,000. Cool. So that's relayer fee percents. LP fee percent is the other component of the fees. This is the fee that you pay for actually utilizing liquidity in the system. This is functionally equivalent to how it works in a cross V1. We have a utilization curve which tracks pool utilization against APY. And whenever you do a relay, we basically consider the integral under the curve over the range in which you're adjusting the utilization. So if you take the utilization from 75% up to 80%, the question really is, what is the size of this rectangle? And we can compute that either like analytically or empirically, like that you can work out the area, and out comes the APY. We spoke about rate models earlier on. The rate model basically takes the number that comes out of this and creates the actual APY that you pay. So the shape of this curve is influenced by the rate model. It defines like the Y offset, the point of the kink, the gradient of these lines, things like those. Okay, so I don't want to go on too much more on that, because if you want to learn more about that, go watch the internal learning session on Across V1. The other component that changes with LP fees is we have this idea of a protocol capture fee. So the basic idea of this is that some percentage of the realized LP fee percent can be siphoned off and sent to the protocol. So this is functionally equivalent to how like X sushi works, where you deposit sushi into a staking contract. Some percentage of the swap fees goes to X sushi holders, and basically those fees are redistributed in the form of X sushi being worth a more than one sushi. So the redemption rate of X sushi to sushi goes up. In the beginning, this is set to 0 and across this percentage, but we can change it. And the whole point of this is that the DAO can govern how we redistribute these things. So we have the ability to do this. It's set to 0. Maybe we turn it on later, maybe not. Who knows? Okay. So let's quickly touch on one more detail about relayer fee percent. So we spoke about how it works earlier on, that there's only one number and that it kind of is ignored in the case of slow relays, all of that. But let's talk about how this thing is scaled. So across V1, we set the relayer fee percent to only cover the gas costs of a relay, right? i.e., a 1,000 USDC relay would cost the same as a 100,000 USDC relay in dollar terms. And that means that the profit yielded by the relayer is the same. Now that's bad, obviously, because the incentive to run a relayer with a lot of capital is low, right? Like the best thing to do in a cross V1 was to relay the smallest relays possible, right? Because they always would give you like the maximum amount of dollar returns with the minimum amount of capital. In a cross V2, obviously we want this protocol to scale and for different relayers to come in and actually participate in the system. So the way that we've achieved this is by scaling the relayer fee percent as a function of the relayer size and the cost of capital at that moment in time. So that's what this equation says, right? The relayer fee percent is proportional to the gas spent, which is across V1, plus this new component. And this new component is the relay size. How much money am I actually using? Times by some cost of capital constant, right? Which is trying to proxy what is the value of money right now, the time value of money right now, right? If it's a chill day and, ETH is not busy collapsing down to $5, then cost of capital might be low. But right now, if you try to use the bridge, cost of capital should be high, right? You could be deploying that capital somewhere else. You could be doing liquidations. Who knows? Cost of capital number go up. In practice, though, actually coming up with this cost of capital component is kind of hard. And the reason is that we don't know how much capital there is in the system, right? In the sense that I might be running a relayer, but I haven't told you how much money I'm willing to dedicate to relays. UMA might run a relayer, some VC fund might run a relayer, and collectively we don't know what is the total amount of money that's available to the relayers versus how much is currently being utilized versus how much could be deployed if the fees went up, right? So there's no like easy proxy for this number. So the design that we've gone for to try and simplify this, which is kind of a good enough metric, is to proxy the relayer fee percent, the realized LP fee percent as a proxy for the relayer's fee percent cost of capital. So what that means is if the pool demand is high, right, all the funds in the USDC pool are currently being utilized, then it's probably likely that the demand on USDC at that moment is high, right? If the demand on the USDC pool in a cross is low, right, like it's 5% utilization, then it's probably likely that the demand on relayer capital is also low, right? This might not necessarily always be the case, but it's kind of like a good enough proxy, and it's kind of the only number we really have. So what we do is we take the realized LP fee percent and we scale it into a number that represents a relayer fee percent. Okay, so takeaway from the slide, relayer fee percent in a cross v2 should have more incentives for relayers. This is going to be the hardest problem with the cross v2, is getting relayers to come online. And if we pay them more money, then they'll probably do that. Okay, silly slide on the relayer bot just with some of its components. Don't need to dig into this. It just does a lot of things with a lot of different clients. Data worker diagram is even worse than this one. So we're at the end of all the content. I'm just going to go over 2 hard problems and then we can open for questions. So the first hard problem that I've already identified is that we are going to run out of relayer money, right? This is going to happen if we have any kind of meaningful demand. The reason is that this whole design, the reason it works so well and is so efficient is that all we have done is moved the capital requirements and the capital efficiency problems onto the relayers. So the relayer, when they run out of money, we then have to slow relay, which is a bad UX. Or more relayers need to come online, right? You can have money in the pool, but if the relayers don't have money, then you can't actually have the benefits of a system like a cross where you have near instant transfers. So this should be solvable with 2 main things, right? The first one is incentives. If we pay people enough money to run relayer bots, they will do it. If you put a 30 or a 40 or a 20% APY on running a USDC relayer, people will do it. The second solution, which we're currently thinking about, which is really hard, but we're thinking about it because it would be a game changer for a cross, is this idea of a community relayer. So the idea with a community relayer is you can deposit money into a pool and then a centralized operator operates the relayer on your behalf. This is basically like Lido, which is staked ETH, a centralized staked ETH provider, but for a cross, right? And in Lido, that's STETH, right? The single largest liquid staking derivative is Lido. And we could create, or a community could create, something like this for a cross where people dedicate capital to a relayer. Now, obviously, the big issue with this is the trust assumptions. You have a centralized operator who's running the bot. They could steal all the money. That's hard. Also, we don't want to run this at UMA, right? Because like there's liability and also associated risks. And also like the protocol is meant to be censorship resistant and permissionless and all these nice decentralized words. So hard problem. Maybe there's like a centralized KYC version of this. I don't know. But yeah, that's like another option that kind of solves the complexity with running out of capital. The last point I'll make is I think you've gathered by now, this thing is complicated. This means that building out these systems was difficult, which is cool. It was a nice challenge, but it also means that reasoning about some of the components is hard. And we're going to need to work on ways of simplifying how we think about this. We've tried as much as possible in the design of every element of the system to simplify how things operate, even though the underlying design is complicated. But yeah, that's a hard problem. Also, upgradability as a result of this complexity is kind of hard. For example, what happens if you upgrade a spoke pool while one of the bundles are in liveness? There's all these like weird edge cases that come about as a result of that. Anyway, those are the hard problems. I'm sure that you guys will identify some more when we go through some questions. Got some more resources here if you guys want to dig into this. I'll obviously post the slides. And yeah, the main one that I would recommend looking at is the UMIP if you haven't already, which has a bunch more technical details on how the protocol actually operates and how everything fits together.